Read the title again. This is the equation that relates work and energy. It's on your formula sheet. Go find it so that you know what we're talking about. In fact, I think I even labeled it. It was that important. I don't always do that, but I think I actually said the work energy theorem. Did I not on the formula sheet? So we said energy was the ability to do work, the ability to apply a force over a distance. The work energy theorem, well, the first definition of work, Anna, was work equals what times what from your formula sheet, a couple of lines up. What did we say work was equal to? W equals times distance. That's the lamest definition. It's the easiest because it's the least amount of typing, but the force has to be a constant force. It's very limited. Work is also the area underneath a force versus distance graph. I've talked about that. I've made an executive decision because we're pressed for time. I'm not going to assess you on that, Hudson Cole. It won't show up on a quiz. It will show up next year on your test if you take Physics 12. The best definition of work, the most writing, unfortunately, is the work energy theorem. If you want to know how much work has been done on an object, how much energy that object has gained or lost, that's going to be the change in potential energy plus the change in kinetic energy. Oh, and Hudson, what's change in anything? Top left corner of your green sheet. Final minus initial. Okay? I'm starting to abbrev. By the end of the year, hopefully we can do some good abbreviating. So I'm just going to jump on in. It says this. A cyclist weighs 65 kilograms. Her bike weighs 7.2 kilograms. You know what? What's the total mass? I'm waiting for somebody to type it in, but 72.2. Okay, I'll take that. 72.2 kilograms. If she's pedaling over level ground, underline the phrase level ground. That's important. Ooh, Christina, what's this asking me to find? How much what? No, careful. How much what? Work. Okay. My first thought, Christina, don't write this down. Don't write this down. Don't write this down. My first thought would be, well, that. But coming back to you, Anna, read the question. Do you see a force in newtons anywhere? Do you see a distance in meters anywhere? I would hear the sound of a record needle getting dragged over the record, and I would say, nope. My next thought would be to look for a force versus distance graph and find the area underneath it. Do you see a force versus distance graph? As a last resort, I move to the work energy theorem. Write this down. Christina, what two words did I underline? Level ground. What do you think the change in gravitational potential energy is going to be if you're on level ground exactly as a number? Okay? I can say, ha ha. Hudson, what's change in anything? And what's the equation for kinetic energy? I'm going to try and do two steps at once. In your mind, can you imagine KE final minus KE initial? But I'm going to write it as a half mv final squared minus a half mv initial squared, because that's KE final minus KE initial, but I did two steps at once. Do the m's cancel here? Is there an m in work? No. In other words, it takes more energy to pedal a heavier person and heavier bike. Let's crunch our numbers. It's going to be 0.5 times 72.2 times 5 squared minus 0.5 times 72.2. Oh, I guess because my initial speed is 0, I can get rid of this whole term. In fact, really what I could have done if I've been looking at my numbers closely, Nolan, is I could have said, ha! Can you all please crunch that? How much energy, how much work, how much food energy from this person riding this bike was required for this person to go from 0 to 5? 902.5? Is that right, folks? Units, energy, joules. Okay. By the way, going from 0 to 5, Allie, by how much did she increase her speed? 5 meters per second. Okay. In B, Allie, going from 5 to 10, by how much is she increasing her speed? Are we going to get the same answer as A because it's a 5 meter per second increase? This is where I told you that square dominates your life. We're not going to. We're going to do the same thing. It wants to know how much work. Allie, we would say work is the change in potential plus the change in kinetic. Then I would say, what two words did I underline? You would say, and I would say, what does that mean the change in potential energy is? And you would say, and I would say, what's changing anything? And you would say, and we're going to get work equals a half mv final squared minus a half, fellas, v initial squared. Thank you. It's almost the same, except v final is 10, and v initial is, in part B. Okay, still a 5 meter per second increase, but watch what happens when I go 0.5 times 72.2 times 10 squared minus 0.5 times 72.2 times 5 squared. You do not get 902.5. Can you all, every one of you, type this into your calculator? And in fact, I'm going to type this into my calculator as well. And bear with me for one moment in time. So if I go to my calculator, I get 0.5 times 72.2 times v final 10 squared minus 0.5 times 72.2 times 5 squared. Allie, what'd you get? I think you're going to get in the thousands. I think in the 2000s, but don't quote me on. What'd you get? 2707.5, yes? If you're driving a car, Brett, and you're paying for your own gas, to go from 60 to 65 kilometers per hour is cheaper than to go from 65 to 70. You're spending more money. The faster you go, once you're going fast, the worse you're burning the gas money. Let's do the next one. I think the next one, Annie, is the same as part B, except what's V final in part C? What's V initial in part C? You know what? It's going to be exactly the same thing. We're not going to write anything. Get your calculator out and see if you can just backspace and edit. Change the 10 to a 15 and change the 5 squared to a 10 squared. Again, it's a 5 meter per second increase. Looks like you are ending up on YouTube, just not in the way you planned. I get, is it 4512.5? So how does this affect all of you if you're doing anything athletic? Once you're going fast, to increase way more energy, it's way more tiring. You're burning way more joules per second. Okay. Let's do a little rocket science. When we launch a rocket, what we're really doing is we're doing work on the rocket. We're giving it potential and kinetic energy. So a model rocket reaches a height of 340 meters when launched. If the top speed of the rocket is 85 meters per second, how much work does the rocket engine do on the rocket? How much gunpowder, it's not gunpowder, how much solid booster rocket fuel energy do we need to do this? And you could make these numbers much larger if you wanted to do like real life commercial rockets. What's this, Blake, question asking me to find, Blake? Do you see a force or a distance? Well, I kind of see a distance, and I might say maybe the force is mg, but they also gave me this 85. This is a job for the work energy theorem. I'm going to say, okay, work equals the change in potential plus the change in kinetic. This time there is a change in height. There's going to be a change in potential, and there is also a change in speed. What's change in anything? What's the equation for gravitational potential energy? Everybody? mg. What about kinetic energy? I want to try, because it's Friday, last block, to combine several steps. I'm going to say, you know what? I think this is going to be mgh final minus mgh initial. There's my change in potential, plus a half mv final squared minus a half mv initial squared. There's my change in kinetic. I did a big plus sign so you could kind of see where I separated the two terms. Is that all right, Blake? Are any of these zero? Now we're visualizing the rocket starting on the ground and going up. Did I say on the ground? Yes. And before we launch it, how fast is it traveling? The gunpowder, the rocket fuel, is going to get turned into kinetic and potential. How much, if this is what we want the rocket to do, if we want it to hit a top speed of 85, and if we want it to get 340 meters into the air, this much. It's going to be 0.15 times 9.8 times 85 plus 0.5 times 0.15 times, no, not times 85, Mr. Dueck. The height is 340. Read the numbers correctly. Wow. Now you're on YouTube, Mr. Dueck, for the wrong reasons. The 85 is the V, and that's going to be squared. How much energy does this solid rocket booster engine have to have in order to do this? And then if you know how much energy you get per gram, now you know how many grams of rocket fuel to put in your engine. And if you go work for NASA, you just scale this way, 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 way up. 0.15 times 9.8 times 340 plus a half mv, don't forget the squared. I'm getting 1041.67. I'll call it 1042. I will say, although I love rockets, I don't know if I like this question. I kind of like example 3. Really what I like, I think, is example 4. But let's do example 3 first. Charlie, a car is traveling at 35 meters per second over level ground. Oh, level ground. Charlie, what's my change in potential energy going to be? Let's remember that. We'll put that in the back pocket. Charlie, what's A asking me to find? Work, you say. My first thought, don't write this down, would be to go force times distance. Why would I immediately erase that in my mind? Or distance. My second thought would be to use the area under a graph. Did they give me a graph? So I'm going to use the work energy theorem. I'm going to say it's going to be the change in potential plus the change in kinetic. Except level ground, what did you tell me the change in potential was? Nothing. What's change in anything? What's kinetic energy? A half mv squared. So my next line, Charlie, I'm going to write a half mv final squared minus a half mv initial squared. Are any of these zero? Careful. Which one is zero? Initial or final? Yeah, come to a stop. Underline stop. Final is zero. We're going to get a negative answer. We should. What it's saying is the car has to lose energy. So it's not a direction concept. It's got to lose some energy. So it's going to be negative 0.5 times 1250 times 35 meters per second. That's about 100 kilometers per hour. That's right around freeway speed, a little faster, actually. How much energy must it lose? You're going to get a number, I think, in the 100,000s. Hudson, you with me? You're doing this on your calculator. You're not foolishly just doodling on the little cool screen or anything, are you? Cole, Hudson's not allowed to play with your calculator anymore. Okay, Daddy says Hudson can't play with it. Listen to Daddy. What do you get? Read me the digits. -7. Yeah. Joules. -765,625. Negative, basically 750,000 joules. Where does all that energy go? It's got to go somewhere. The laws of conservation of energy says you can't just magically make it vanish. It has to go somewhere. Where does it go? Heat. If it's an internal combustion engine. Where does it go if it's an electric vehicle? Most of it cleverly goes into recharging the batteries. This is why, as soon as Priuses became available, I don't know, you get probably too young to remember, all of the taxi fleets switched over to Priuses very quickly because every time they're coming to a stop, they're recharging their batteries. A Prius or a hybrid is not that much better than a gas motor if you're driving in the prairies where there's no traffic lights and you're driving long distances all the time. You won't get a big savings. But if you're driving in downtown Vancouver where it's stop and go, stop and go, stop and go, every time you come to a stop, rather than wasting this energy as heat like a regular engine, you're bleeding a whole bunch of that back into recharging the batteries. My friend has a Chevy Volt. He lives in Mission, but his daughter lives in Kelowna, so he takes the Coquihalla to go see his daughter all the time. He always tells me, I know as long as I can get to the top of the Coquihalla, even if I only have like 1% battery left, then I'm fine. By the time I get to the bottom, I'm fully charged every time. Why? What kind of energy is he losing as he goes downhill? It's got to go somewhere. Goes into recharging the battery. Okay. B. I kind of like B, except I'm going to expand on it in example 4. Malcolm, what's B want me to find? Nope, before that, there's a phrase. What? Force. I mean, I guess F equals what? But I don't see a time. I mean, you know what? What did we find in part A? I'm looking for a word that starts with the letter W. Anna, what was the version of work that had an F in it? Yeah, you got to sit up and read something from 5 minutes ago, but I planted the seed. You got. Okay, here's what I'm going to say. Force times distance equals -7,565. That's what I'm going to say. By the way, which force is it that brings the car to a stop? We've talked about this as why you can't stop on ice. Yeah, it's going to be friction. Malcolm, get the F by itself. Yeah. By the way, we probably could have got there. There is probably a way we could have found the acceleration, but one line, here we are. Divide by D. So go answer button divided by 82. You put it face down in the appropriate block. Thank you. What do you get? You get a negative. Now, in this case, the negative force is a vector, so this is a direction. If the car is moving forward, which way must friction be acting to bring it to a stop? Be obvious. Okay, so I'm okay with this negative as a vector now, too. It's telling me, yeah. What'd you get? 9367. Is that rounded off properly? 9337. Rounded off properly. Newtons. And in fact, now I can even ask another follow-up question. Stephen, what is creating the force? Friction. We figured that out, so we answered that. Stephen, what's C asking me to find? Hey, what's mu? I don't know. What's mu with you? Yeah, it's good. What did we just find in part B? Friction. So now, hey, is there a version of friction that has a mu in it from your formula sheet? Going back a couple of units. Yes? How would I get the mu by itself? I don't know the normal force, but can you imagine the free body diagram? What do you think the normal force is the same size as in this free body diagram? Yeah. So Mu is going to be answer button divided by, Stephen, I've scrolled down. What was the mass? 1250? And G, you've memorized out of laziness. You have memorized it out of laziness. G? Yeah. Now, here, if I use my answer button, I'm going to get a negative mu. That's stupid. I'm going to ignore the negative because coefficient of friction, it's just a ratio. It's neither negative nor positive. So this is where I would just finally actually ignore a negative. You'll need brackets around the bottom. And I'm hoping, because I was making these numbers up, I'm hoping you're getting legitimate car tire numbers, which are usually in the 0.6, 0.7 range, I hope. What'd you get, Stephen? I'm going to ignore the negative. It's on my calculator, but the coefficient of friction can't be negative. 0.3 sig figs. Point what? 0.762? Units. Nothing. Yeah, coefficient of friction has no units. Okay. That was kind of the teaser. I like example 4. I like example 4. This is the promise that I promised you way back in October. In October, we did a crime scene, a crash scene investigation question where we asked whether somebody could be charged, except I had to have the cell phone pick up the sound of the skid, which was so dumb. That would never happen in real life, and you don't need it in real life. I like example 4. I like example 4. I like example 4. An RCMP officer is investigating a crash. A car has struck a pedestrian at a school crosswalk. It's a hit and run. So no witnesses, and the pedestrian doesn't know what the car was. The officer measures the coefficient of friction at the accident site to be 0.65. They have a device, they drag it along the pavement. It's got a scale and a needle. That's how it tells them, it moves along a scale like a bathroom scale. It shows you the coefficient of friction. And he measures skid marks that are 45 meters long. Should the RCMP press charges against the driver? What do you think this question is asking us to find? What's going to determine whether or not we press charges? I apologize, I got something on my screen. I've been trying to grab it, not working. Now my touch screen is working. Here. What's it asking us to find? What will determine whether or not we press charges in this car accident? Well, the hit and run, first of all, but really what we're asking now is, how do we know who's going over the speed limit? What are we looking for then? Which one? VI, because what's VF of every car accident ever? Okay, so, yes? And I notice they've given me a coefficient of friction. How am I going to solve this? I'm going to solve this by being stupid obvious. I'm going to write a statement that no one can argue. I'm going to say work equals work. That has to be correct. But now I'm going to use Anna's equation for work. Anna, that's your line. Which force, if we're talking about a car stopping? Which force, folks, if we're talking about a car stopping? Okay. Force of friction times distance, that equals the change in potential plus the change in kinetic. If I give this to you, when I give this to you on a test, I'll include the phrase level ground. Does this question mention a hill at all? No, but in real life, if you measure the height of your hill, you can include that and still be very accurate. So this will even handle not on flat level road. This will handle on a hillside as well. We're going to assume there's no change in potential. What's change in anything, Hudson? So it's going to be force of friction times distance equals a half mv final squared minus a half mv initial squared. Which of these is 0? The first one. That's not a physics term. Which of these is 0? VF, right? Now, Luke, what that's going to give me is a negative answer on the right-hand side. because we're losing energy, we should put a negative in front of friction because it's in the opposite direction of the way we're moving. And what I'm really saying is on my next line, the negatives are just going to cancel out. I've got a negative equals a negative. Who cares? But I'm not just magically making the negative vanish, Jet. I'm understanding each one in a different context and saying they are there. Okay. Stephen, friction is what times what? I don't know the normal force. Oh, but look. I think I know another force the same size as the normal force. I get on my next line, mu mg, the d drops down. Guys, I need you here. Thank you. Equals, and I'm going to write mv initial squared over 2. I'm not going to bother putting the 1 because, I hit the wrong button. I'm not going to bother putting the 1 because I'm getting towards the end of this. So let me erase that 1. Oh, hey, for me to start my criminal case, do I need to know what type of car it was? What do you notice? What about the masses? They're going to cancel. This is night. In fact, do I need to know if there were passengers in the car or not? No. Do I need to know how much gasoline was in the tank? No. This will all stand up in court. I don't need those details because the M cancels. So they can try any argument that they want. Not a problem. What were we trying to find, folks? How would I get the V by itself? Times by 2 and then? In the same way, Stephen, that you've memorized the 9.8, I'm willing to bet RCMP officers that regularly investigate crashes have probably memorized the fact that in a car crash, if you know the skid marks, it's 2 times mu times g times d square root. I promised you back in October that we would revisit this. We didn't need the fluke of the cell phone picking up the sound of the skid. No, you don't. I've scrolled down. What was the coefficient of friction? 0.65. Gravity, I know, is 9.8. What was the distance stopping? 49. How fast was this driver going when they started to skid? Oh, and what'd you get? 25? Anybody else? Even or 0.9 what? Oh, okay, so really close to 25. So I'm going to write 25 meters per second. Could you multiply that by 3.6? How many kilometers per hour is that? So 90, if this was on a school road or a city road, we can already charge. By the way, that's minimum speed. Why is that minimum speed? Why could they possibly have been going faster? What did we measure? So could have slowed down but a lot before skidding. Okay, so if you were preparing this in court, you would say that's the minimum speed. And of course, nowadays you'd also be looking to see if there's like security camera footage from a business. From that, you could actually infer the speed as well by measuring how much of the road the camera picks up, measure that distance, measure the time going through, all sorts of stuff. But even without that, we can prepare a case. So I like this question. I like this question. I like this question. Yes? And it's a cool question. Oh, I got to show you someone being stupid. Social media has been good to reveal some of the stupidest human beings on the planet. The number of people that have been committing crimes and have decided this will get some clicks and posted online. This is very early. This is from 2006. This was shortly after YouTube became a thing. This was one of the first YouTube videos to go viral. It's from Vancouver Island. You need to all, well, you know what? Put your pencils down, look up. I took this because even though it's 2006, this is probably 240p, not HD or anything like that. It has the speedometer in it, which is, it gave me data. How fast are we going at the front? Can you read the speedometer? Units? Is it? Look closely. Look at the inner numbers. Look at the outer numbers. What are the units? It's miles per hour. Convert 220 miles per hour to kilometers per hour. 354. Convert 220 miles per hour to meters per second, because that's what we're going to want. It's 98.4. Because he's pinned the needle, we're going to round it up to an even 100. That's one football field every second. Okay? Let's remember that. What's happening to his speed? What's happening to his kinetic energy? Where is that energy going? How much? I'd like to know. He's going to slow down to 100 miles per hour. I'd like to know how much energy was lost in doing that. And let's play around with some of the numbers. So one of the things we're going to want is how long this takes. If you have a stopwatch on your smartphone, can you get it out, please? Can you get your smartphone stopwatch app open? Several of you, please. All of you, please. Open up your stopwatch app. You're going to hit start right when you hear the sound change, and I'll say go. And then we're going to hit stop when I say stop when he gets to 100 miles per hour. It's going to take some time, but let me back up. Okay, so everybody has your stopwatch app open. Get ready. Start. Stop. Luke, what'd you get? Luke, what'd you get? 15? Cole? Annie? Check. I'm hearing a little more than 50. Let's use 15.5. We're being pretty rough here. So I'm okay with that. Okay. So here's our data. Time equals 15.5 seconds. VI was 100 meters per second. VF, well, it was 100 miles per hour. I need to get that. Convert 100 miles per hour to meters per second. It says 44 point, you know what? Let's just call it 45. We're doing some rough numbers. Okay, there's our data. Tucker, what does A want me to find? What we're really going to find is the work done by friction. The work done by friction, which is going to be the change in potential plus the change in kinetic. Tucker, you saw the video. Did there seem to be a hill at all in that video? So I think we can safely say, the bike was impounded, but because they couldn't identify the driver, since that person didn't appear in the video, the RCMP figured out what type of bike it was and were able to narrow it down. They did impound the bike. Tucker, what's changing anything? So this is going to end up being the work done by friction is going to end up being a half mv final squared minus a half mv initial squared. Mass doesn't cancel because there's no m in work. I Googled back when I downloaded this video the type of bike, and then I made a guess for an average mass. All told, it's about, what did I say at the top of the question? My guess for the mass was? Okay, again, rough numbers, but just to give you an idea. So it's going to be 0.5 times 300 times VF is 45 squared minus 0.5 times 300, VI is 100 squared. You're going to get a negative answer because this biker had to lose some energy. Try crunching this. The number is pretty impressive. It's going to take up a fair bit of your screen. It's over 1 million, yes? Yeah, I get 1196250. 1196250 joules. Nathan, what does part B want me to answer? Where'd it go? 4-letter word starts with H. Heat. Now, he was using his motor to do a lot of the slowing, not his brakes. If you had a thermal gun, you would have seen his whole motor case getting much, much hotter. Okay? It's got to go somewhere. Heat. Cool. What does C want me to find? Well, I think that's the units. What's the physics concept? Starts with a P. Power. What's my equation for power from my formula sheet? I'll give you a hint. You're looking for a P equals what? Did you get that on your own, or did you steal that from this person blurting it out over? Okay, power is work over time. You know what? It's going to be my answer button. I'm going to ignore the negative over, and what was the time? We said 15.5. So I'm ignoring the negative, 15.5. The negative is just telling me that we're losing energy. I get 77,177 and change. Yes? So I'm going to go 77,177 powers measured in watts. And then just for giggles, oh, Brett, what's D you want me to find? This really cool question that we've been looking at that I think is a really interesting one. You had your chance. Nate, what's D asking me to find? How would I figure out how many light bulbs? Take this number and divide it by. I'm going to go answer button divided by 60. How many light bulbs does it take to change this motor? Well, how many light bulbs does this motor, whatever joke you want to make from this, the answer is, holy smokes, that's a lot of light bulbs. That's a lot of wasted energy. 12,000 or 1,286. Again, this here is why electric vehicles are so much more efficient. Most of that energy goes into recharging your battery. Much nicer. I like the graph question. I'm going to skip the graph question. I'm going to do graphs next year. So your homework, number 1, totally fair game. Number 2, totally fair game. Number 3, totally fair game. You can skip number 4 because it's got a graph. You can skip number 5 because it's got a graph. You can skip number 6 because it's got a graph. You can skip number 8, although it's cool. It's a Friday. You can skip number 9. 9! You can skip number 10. So really it's just 1, 2, and 3. But what I've noticed is I didn't give you another example 4 in the homework to practice. I may throw one on a take-home quiz somewhere. Let me hit pause.